The content of this meeting is being sent to a third party. I'm very worried right now.
To YouTube, that's true. That's the broadcast. I'm assuming. So welcome everyone. We'll wait 15 seconds for the rest of the audience to join us, and then we'll start. Still waiting for my clock to turn 4 p.m. in the UK. Okay, that's just happened. So we are glad you joined us today. Welcome to this edition of Virtual Seminars in Economic Theory. Today we have Andrew Caplin from NYU, and the title of the presentation is Human and Machine Learning, a Cognitive Economic Approach. This is based on two papers with several co-authors, Daniel Martin, Philip Marx, David Deming, Shangwen Li, Ben Weidmann, and Kadachi Jiada Ye. We also have two guest panelists today, Larry Samuelson and Emir Kamenica. We are super happy that you are here. Thank you for accepting this invitation. A word on next week, we have Ji-Hee Yoon from UCL presenting dynamic trading and inference in non-Markovian equilibria, joint work with Marzena Rostek and Xian Wu, and guest panelist Daniel Chan and Piero Gottardi. I just want to remind everyone about daylight saving times. This is happening this weekend in the UK. So if you are not synchronized with the UK time zone, please check your time next week because there might be a discrepancy. Okay, thank you very much again, Andrew. Take it away.
All right, so let me plunge in. The topic is as a human AI value chain. And the typical setting is supervised learning. And in the first stage, humans actually label instances and make them ground truthy. A machine generalizes then in stage 2 from supposed ground truth. And then the human and the machine interact in final decision making. And the ideal is to classify instances correctly and minimize losses. And this is kind of a big area in which we're going to think about optimizing performance of an interactive system. That's what we're kind of where the big money will be. So I'm going to talk about two of the stages. Modeling machine learning is really inside the machine's head, whatever that might be. ABC is on stage 3 when the machine and the human interact. Both these papers are joint with Daniel Martin and Philip Marx. ABC also with David Deming, Shangwen Li, Ben, and Kadachi. And we've got work on stage 1 ongoing, and I just think there's a lot to be done here. The research focuses on systematic patterns in mistakes. And I'm going to make a point, and it will be visible, that a particular data set, ideal, state-dependent stochastic choice data that Daniel Martin and I have been playing with since 2015, will be key in studying these. We're going to be using revealed preference methods in the area of bounded rationality, in which we're really following up on Paolo and Marco. We think that parametric models are premature until we understand model classes. The results are going to be very simple because all you really need to do is say that in particular models, certain things that could have been chosen were revealed not to be. And all you have to think about is what was revealed to be not chosen and find the right revealed not chosen to characterize what the imprint of optimizing theories. And right now, there's something of a two-way trade between human and machine learning models. Larry and Jacob have been involved in reverse direction, where you take a machine learning model and you think how that applies to a human. The first paper, Modeling Machine Learning, exemplifies how a standard Bayesian learning model can rationalize AI behavior. The second paper, done much more briefly, shows that humans do not act analogously, very clearly miscalibrated in their beliefs. There's also a big difference. Modeling machine learning is theory-led, the experiment absolutely follows. ABC is experiment-led, and the questions follow. And I believe that in this area, measurement and modeling will co-evolve. There will be no clear leader. I will prove no theorems and rely on known results, or at least results that when you see them, you'll say, well, that's intuitive. So there's nothing surprising. I don't want to surprise anybody. And I want to answer the question at the end, in what sense is this economic theory and why does it matter? Okay. The formalities are in a very small number of elements we need to have in notation. And that's really all I need, is that you grip the notation. There's going to be a finite set of outcomes, e.g. disease types. In fact, in the case that we're implementing, it will be pneumonia or not pneumonia, then the algorithm is trying to learn about. And it can make predictions, about, e.g., confidence scores of some type for each possible outcome. And in our case, these will be a continuous measure between 0 and 1 of confidence. A loss function, which is actually part of the machine's programming, will specify the value of a prediction given the outcome. And our goal is to model the AI predictions. We're going to model it, and we're going to think about what it shows in data, because we're going to use that to decide, which class of model explain the data we see. The performance is going to be assessed on how well its predictions align with actual outcomes in a labeled data set. Loss function L in the class of such loss functions will generate A1 through AN for a data set of size cap n, typically the test data, in which we're going to see how well it does by producing the joint distribution P sup L of predictions and outcomes. And I want to make a comment on roughly the same moment that Daniel Martin and I woke up kind of disturbed and interested and excited when we realized an abstract data set that we'd been thinking about, which at the time was called P of A omega, the probability of an action in a state, is kind of what is done routinely in machine learning. And I don't know if the phone calls crossed, but very close to, and then we started to plunge and think about this, and every step of the way, Philip Marx got involved. So we're going to take a decision theoretic perspective, and we're saying, there's a whole class of loss functions that we could have fed the machine, and they would have produced different performance data. Presumably, there's some response of the algorithm to what it's trained to minimize. And this is kind of a decision theoretic in the same place that we'd say, let's give people different decision sets to choose from. So we think of varying a whole bunch of things and looking at the trace in the data of what happens. And all the models that we're going to, as if, are Bayesian. We're going to think of a model, an algorithm as having a prior, which is loony, getting signals, which is nutty, forming posterior beliefs, which is ridiculous, using Bayesian updating, which is hilarious, and choosing predictions to minimize expected losses. So we're going to pose 3 qualitative questions, and they're as-if questions, of course. Does the algorithm learn in a manner that is optimal given L? If so, what are the trade-offs implicit in its optimization? And does the algorithm choose optimally given what it has learned? And obviously, our game is the as-if characterizations of these and actually an implementation at the same time.
Andrew, may I interrupt with a question?
Please.
The statement, does the algorithm learn in a manner that's optimal given L? I don't quite understand. I would have interpreted if you had said, does the algorithm predict in a manner that is optimal given L? And I think that's what you're going to do, is look at the predictions and ask if they minimize L. Is there
yes,
something?
yes.
Does the word learn give us something beyond that?
Yes,
Andrew, can you answer that? Because I thought that what you mean by this, and if it's not, it would be helpful to clarify, is it's precisely because you're going to have this as if representation. So you will have a description of the algorithm that actually describes gammas, these posterior beliefs. Now, there actually aren't any if you open up the code and it's not there, but your as if perspective is going to explicitly say, I am interpreting this algorithm as if it had beliefs. So I thought you used the word learn to apply to the beliefs that you are in your as if approach ascribing to the algorithm. I don't know if that helps, but that seems related, I think, to Larry's question.
Yes, that's correct. And it's the distribution of posteriors, that Bayes consistent distribution of posteriors is what we call its learning.
Well, how does that depend on L? Why would learning, why would the posteriors
that's
depend
what
on
we're going to be exploring.
But in general, if it's an as if Bayesian model, why utility function does not impact how I learn?
Yes, it does if I have costs of learning.
Okay, so it's not about whether the posterior is correct given the signals. It's about whether I'm getting distribution of posteriors that is consistent with some costly learning. So it's not about whether the posterior satisfy Bayes' rule. It's about whether distributions of
posterior. We're going to, we will in a way be imposing that the posterior satisfy Bayes' rule because they'll be inferred from the data.
So let me see if I can summarize this. We could rephrase that first question as something like, does the algorithm perform optimally given L?
Yes, maybe. The whole question might be that.
Good.
And we're just breaking it up because it turns out the characterizations are given in a certain order. So thank you, but let me go on and do the as-if characterizations one by one. So here's, there's a little bit of notation. There's a squiggly Q. This is Emir and, everybody who does Bayes' rule writes this thing down in some letters. We're just using capital Q to be the distribution of posteriors averaging back to a prior. A gamma is an individual posterior. We're going to imagine that the algorithm has a probabilistic prediction function, which says for any posterior it ends up with, it ends up producing a Q of A given gamma. How likely is it to pick A given gamma? It's a mixed strategy. Now, we're going to be thinking of it optimizing in its predictions. So this is that we're going to now think that, imagine we were thinking of an algorithm that really was a Bayesian. We'll say, well, what it would do in Q hat of LQ, the second line, given any loss function and any form of learning, it would pick its predictions to minimize expected losses, which is that big triple sum on the right-hand side. Summing across the things, the truths, summing the Y's, summing across the A's, summing across the gammas, according to how likely they are. And its strategy will be both what it learned, Q, and what it did given every posterior that it learned. And that will press out into a data set, which will be what that form of learning and that mixed strategy would imply for the joint distribution of predictions and outcomes. And that's the third line. We'll open with a question about, is there optimal choice given learning? And what we're going to say then is that P super L will have a signal-based representation if we can find a prior, a Bayes consistent distribution of posteriors, and a prediction function such that the prior is correct, you're doing rational expectations, predictions are optimal at all posteriors, and predictions are generated by the model. So that's all just uses the symbols we just came from. So is there something that the machine might have learned, at which point it would have been choosing its actual predictions optimally? And it turns out that using results of Daniel and myself, or Bergerman and Morris, there's a simple check in the data which that this has been done, which, let's just look at the definition. Performance data PL is loss calibrated to loss function L if you cannot, by a wholesale switch of predictions, reduce losses according to L. So if you look at the expression, it says A should be minimum among all A primes, every switch you could have made, based on the data P sup L associated with A, but switching the loss function, the A to A prime, a different prediction. So let me just read that again. It must be that every prediction A that you made was among those that would have minimized the expected losses given essentially the data associated with A. So you can't find some wholesale way of switching prediction that reduces your expected losses. And the known results are that P sub L has a signal-based representation if and only if its predictions are loss calibrated to L. So there's nothing new about that result. And the key counterfactual is to imagine switching predictions to feasible unchosen alternatives. Testable condition is no wholesale switch of this type can be loss reducing. And only wholesale switches need to be thought about because they're the only things that are clearly informationally feasible. I do not know whether the algorithm knew something beyond what essentially is the revealed posterior associated with a given prediction. But it could certainly, whenever it made prediction A, have switched it to A prime feasibly. And if it didn't do that, presumably because there wasn't a strict loss reduction at stake. We're actually going to now show how one can.
Andy, I'm going to interrupt for 1 second, just in what I think of as a potential role of the panelists. I think there's a small chance, but small is big enough, that people not deeply familiar with your earlier work, not going to be immediate, not be 100% clear that how you're using the word wholesale. So I just want to interject and avoid any sort of curse of knowledge. Wholesale
I was about to ask the same question.
So wholesale just means there are two actions, an action A and action A prime. What a wholesale switch is, I used to do A some of the time. Now, whenever I do A prime instead. That's the wholesale switch. That's what the word wholesale means, is like I just take instances of an action and take a distinct action instead of that in all of such instances. That's the meaning of wholesale, if I'm correct.
You are correct. And the idea is that is in a Bayesian, in a world in which this person really was a Bayesian, they, quote, knew the posterior, they knew they were picking A. Whenever they picked A, they could have said to themselves, let me pick an alternative. I don't know of any more sophisticated strategy they could have picked based on some deeper knowledge they have. That's not revealed to me. So we've got to stick with wholesale switches if we want to make sure we remain informationally feasible. And that's the nature of the result. It's familiar, it was, anyway, so. And this is kind of the nature of the revealed preference logic in state-dependent stochastic choice data. You pick something that's informationally feasible or feasible according to your theory and say it can't be improving. And I want to point out that in the particular case we're looking at, not globally, we happen to take the following as our first exemplar. We have done no monkeying around. it's very hard to find good data sets that you can play with. And we're using deep latent chest X-rays. It's a very famous data set with a very famous date code and many uses. And it's pneumonia, not pneumonia. They train the model with beta-weighted cross-entropy loss functions. This is very standard. They actually use class weight 0.99 in their own work. And their logic, which is a bit wacky, is that there aren't many pneumonia cases. There's only 1% of cases of pneumonia. So we better boost the losses associated with not identifying pneumonia. And that way we're going to get what we think is good performance of the algorithm. And we're going to show that that's not very good logic. We're going to vary from 0.7 to 0.9 to 0.99 as our 3 betas. And we're going to show this is what you're supposed to do. These aren't proper scoring rules. So you're supposed to misrepresent your beliefs and give a confidence score that might be 0.999, even if you're only 0.7 sure, if you've given it. So this is a plot of the how to misrepresent your beliefs. And in fact, they do misrepresent their beliefs almost exactly that way. So we effectively, it looks like they are loss calibrated in this data. And now we're going to move on and see what else we can find out.
Sorry, can we pause here just for a second?
Yeah.
To an economist, these betas would never come from anything having to do with prior tendencies of pneumonia. As you said, that was crazy. They would come from the medical cost of type 1 and type 2 errors.
Yeah, exactly.
Of diagnosing someone with pneumonia when they don't have it, which is not going to be negligible. Maybe you give them antibiotics and they don't need them, versus you think that they don't have pneumonia and they do, in which case you delay antibiotics. So there is some true beta, no reason to think it's 0.5, that is the loss to the patient.
Well, there's a larger class of loss function discussions that should be had. They should be working more within the class of proper scoring rules, I believe. And they should then think about the losses exactly the way you said. So there's a whole different logic they could be used. If you look at the reasoning used in machine learning for selection of a loss function, it's uniformly cockamamie. It just makes absolutely no sense. But they've tried 6 billion and they probably won. They did something right, but there's no logic to it. It's very disturbing. But they're winning, so they don't really care. But yes, so we think, okay. And now what we're going to do is move on to what they learned. What did the AI learn as a function of the 3 different loss functions we gave it? And we're going to do what we think is the folk wisdom, which is the algorithm capacity-constrained learning. The algorithm chooses among a feasible set of signal structures. We think that's what they might have had in mind for a model of the machine. They don't bother modeling the machine, so it's not a conversation you can have. And the second one we're going to bear in mind, because we like it, is the algorithm chooses among signal structures of different costs. E.g., it allows more informative distributions to be more costly and may not pick them if the incentives don't point that way. I have to tell you that we picked these because, you know, the first one is natural and the second one is rational and attention. We had no particular reason to believe that rational and attention would be a better model, but it certainly seems conceivable. And so we just wanted to explore what's going to happen when we do this. And there's going to turn out to be a very clean answer.
Can you say a couple more words about the first one being folk wisdom? So my understanding is you're about the first to think about machines in this revealed preference way. And so I wonder, where did the folk wisdom come from? Or who are the folk? Or
I think that when you talk to people, we've tried to run conversations. The second one has their eyes glazed over. And the first one, they say, well, it's doing as well as it can. And if you kind of like, what's the word doing as well as it can? It's got a certain number of operations it can carry out. It carries them out and it does it as well as it can. And so that kind of like, I don't know what that means, but it could mean capacity constrained. It's as close as I can get to what they mean.
Yeah, all right.
All right, so now we're going to allow learning to vary. And we're going to define a large strategy space, which is you can learn anything and you can pick any mixed strategy. Now I'm going to think about, for a given loss function, if there is in fact a feasible set Q star, I can identify a class of optimal strategies by looking at the right-hand side and minimizing losses that way. Correspondingly, there are optimal data sets, all of the things that would get compressed out of the optimal strategies. And an algorithm is consistent with capacity-constrained learning if there exists some feasible set and that would produce the data that you actually see out of the machine as a function of L. And I'm going to now take a characterization of capacity-constrained learning from an incompletion paper. And the reason I'm saying the result's known is because in a way it is. I mean, in a way, this is a first statement of it, but in a way, it's so naturally what you'd expect that it isn't quasi-known. What we need to do, as always, is think about more than one loss function. If you're going to do a nice reveal preference exercise, you need to see choice in different choice sets. In this case, you need to see losses for different loss functions. And there will be L super M and data sets will be P super M. And we're going to produce one Q matrix, a value of learning matrix.
Andy, can I interrupt you there?
Yeah.
It seems I think you're almost maybe not advertising this as most compellingly as you could, because you could have actually done with this in this context different choice sets, different menus. You could have varied the data, so you could have keeping the utility function fixed. So I do think there's actual. It is a rather a conceptual leap, and I think a notable one worth sort of shining a brighter light on.
Oh, thank you.
Instead of thinking about varying menus or varying the training data set, you could have done various things that you vary.
Yeah.
This idea of varying the loss function, I think, is I think nice.
Thank you so much, Emir. When you're in the middle of something, it's the curse of familiarity. I have no idea. We arrived here and here we were. But thank you. So we're going to vary loss functions and see how they impact the data. We're going to then do the following. What's cap G super M N? Well, what we're going to do is wholesale replace any prediction A with any alternative A prime. What we're doing is switching loss function M into the data associated with loss function N and minimizing losses in the switch. And I think you can sense why we might do that. Like, oh, look, I see that data set N involved certain different type of learning for loss function N. Maybe with loss function M, I would have lower losses if I'd switched to N, or maybe I'll have higher losses. But I certainly have some loss reflected in GMN. And this is, maybe a basic insight in this reveal preference approach is the extent to which you can switch learning between decision problems. Because learning is to some extent revealed in the data. So this is said, look at the learning that was done with dataset N and use loss function M, compute this entire matrix. Once you've computed this matrix, ask yourself if there was ever a switch that lowered losses. There shouldn't be if there is capacity constrained learning, because you could have used the revealed other learning apparently for this just as well. So it's only an algorithm is strongly loss adapted if the entire matrix is greater than or equal to 0. And that is a necessary and sufficient condition, in fact, for the capacity constrained learning. And the counterfactual is simple. Can't be possible to lower losses with learning revealed to be feasible for a different loss function. Now we're going to do what seems wacky. We're going to invent a cost function as an as-if object. And we're going to call it a pseudo cost function because it's not costing anything that we understand. But if it were to exist and be a cost of learning, then you would say, look, it adds to the losses. The costs add to the losses. And so what I should be doing is minimizing the sum of the expected losses from the learning plus the cost of the learning itself. That will give me a set of optimal strategies from which I can press out the data and ask myself, does the data look like there's some cost function for which I minimize the sum of losses, both direct and indirect from and it's consistent with costly learning if we can find such a cost function. And the key counterfactual here concerns cost-preserving switches in learning across decision problems. It's a different counterfactual. So what we're going to do is define HMN as all sequence of indices that are all distinct except possibly for the first and last element. And they go from M to N, and they could go from M back to M itself. Now we're going to think about shifting learning in a cycle. And in each case, we may end up in some switch lowering losses, but in the next one, maybe we raise it more. So we're going to take up the sum of all the sum of all the first changes across the path and say the algorithm is loss adapted if you can't conduct such a cycle and lower losses in a cycle. And that is essentially the no improving attention cycles condition of Caplin and Dean, which says an algorithm which has a signal-based representation being loss adapted is necessary and sufficient for costly learning representation. So we're now got our two models. We've got two testable conditions that come from matrix algebra. And in fact, the counterfactual, of course, is to rule out loss reduction in cost-preserving cycles of learning. This is tightly analogous to the strong axiom of revealed preference. I mean, really strongly analogous. So much so that you can use the Floyd-Warshall algorithm to the complete directed weighted graph with edges D0, Mn, and compute the D matrix. And the algorithm is loss adapted if and only if the candidate matrix has a zero diagonal. This is completely implementable and operational in the same sense as the standard axiom of revealed preference.
Andrew, let me ask a question about cost functions.
Yeah.
You explain in the paper that the capacity constrained model is a special case of the cost function model, because you can always choose a cost function that kills anything that you want to put outside your capacity constraint. So that's a nice observation, but it also suggests that if you place no restrictions on the cost function, you have quite a bit of freedom to do things. And so we might be interested in cost functions that satisfy some properties. A monotonicity property is one that comes to mind. Do you have any idea when, in the end, you tell us that your results are consistent with costly learning, you could go further and say your results are consistent with costly learnings with a cost function that satisfies, and then
Emir knows the answer.
Fill in the
Yeah,
blank.
this is all in the original paper of Caplin Martin. This is the monotonicity you get for free, zero information you get for free. Anything that's rationalizable is rationalizable with a sensible, meaning monotone normalized cost function. And again, that's not new to this setting. That's from the previous paper about the identifying rational inattention. But on a related note, and like we know, of course, from this observation that the costly learning model has to fit weakly better than the capacity constrained model, because in a sense it's more flexible. And is there, before we see the empirics, there's a sense of like, well, how much is a lot? We know it has to do weakly better. So there's a bit of sense of, it's like I'm comparing, like there's no analyzed statistics. You say, okay, you estimated a model with 7 parameters, I did it with 2, you're going to do better than I do. But like, what's the right penalty to apply for the quality of fit when I know you're going to have to do better, allowing for any cost function?
I agree. It's such a shame that Philip Marx isn't here because he could answer that question. I'm moving on. I don't know. I think these are great questions. I actually think these are quite tough tests. You're going to see what happens. And we were surprised. I just tell you that we were surprised. That doesn't mean much other than we were surprised. So is there a capacity constrained explanation? No. This page says no, there isn't. It says so in the small decimal places, but it says no. And in fact, there's a reason, which I'll go into in a second, which the reason is in the fact that this is the second question has the answer yes. Is there a cost? Does it look like there's a cost-based explanation? The answer is yes. And that's because of a really coherent pattern, which is it looks like the learning is better for the more equal weights. It actually looks like it learns better for the more equal weights. So to rationalize not picking the learning corresponding to the more equal weights, it has to be more expensive. And that is, in fact, one can characterize the setting, the qualifying costs, all of them can be computed off the matrix. And you normalize to the cost of the bad learning being 0, you can nearly point identify how much more expensive it is to learn the 0.7 and 0.9. So something is going on in which the 0.99 is just a really bad choice. It results in crappy learning. That's what's happening. And to rationalize it, it has to be that was very cheap. And there's nothing to do with real costs. So I know what these pseudo costs are, but they're not real costs. We actually have moved a little forward in our understanding of what's going wrong. I won't share it because it's not complete. But it provides an interesting take on the world famous alignment problem, in which the most famous line right now is that humans want to, machines, if we give them incomplete instructions, want to turn us all into paper clips. And so what we need them to do is to learn what we like and dislike. And it turns out that might not be quite enough because we don't know what the machines find costly or difficult. We'll want to understand what's the performance of this learner. We should understand a little bit more about its as-if cost function. So I'm now going to, roughly at the right time, move on to an entirely different piece of work. A very different basic method and a very different moral. In the end, this machine, however it learns, will produce some output. It will hand that on to a human decision maker. The human decision maker will do something with it, and out of that will come a diagnosis in a hospital and many, many other things. So the human AI interaction is what everybody in labor economics is freaking out about right now. And the question that David Autor, and Darren Acemoglu, the kind of things that are of most interest, is what will happen to the value of skills when people are working with AI, and in more generally, what skills will be valuable. And so you're now going to see me make a real pivot into labor. I'm going to put my labor economics hat on and ask a different question. What skills might be valuable for a human being working with an AI advisor? And the typical answer to date has been one thing that's going to happen is that the AI advisor appears to make the lower skilled people better approximate the higher skilled people. And therefore, there is a thought that this could compress some skill-based differentials. In this paper, the ABCs, it's called Ability, Beliefs, and Calibration. We're going to do something which is a complete riff on where we just were, and we're going to say that human may not, in fact, be Bayesian themselves. They may have miscalibrated beliefs. An overconfident individual will be certain about something, even when they're often wrong. And the underconfident will think they know less than they in fact do. And our question in this paper is, do those with better calibrated beliefs make more effective use of AI advice? And obviously, it seems highly intuitive that it might. And I'm going to show that in our little example, it in fact does. The challenge here at the moment is not theoretical, and I think that's an important point to make. I mean, we could model an AI, somebody who's non-calibrated working with an AI. In fact, we developed a number of models, and they're very sophisticated and interesting and confusing, but we didn't have any facts to play with. So we thought, let's generate a little bit of how a human and an AI advisor interact. And what I'll show you is results that indicate there's a little bit of a way to go before we know how to begin theorizing about this, I think. I don't know what more measurement to be done, but I think we need even more. The experiment is here what led. What leads is we know what we want to do. We want to set people up so they have a task in which they give probability assessments in a setting in which there's a clear ground truth. We want many, many participants. So we want many reports per participant. We want the right level of task difficulty. We want people to report widely across the probability scale. And so, this is a tough design problem. And Kadachi and Shangwen in particular did a very good job of coming up with a setting in which we believe many of the conditions were passed. What we're going to do is focus on human deviations in the following task. In each of 160 rounds, participants are presented with an image of a human face. They're asked to report the probability the individual was over 21 at the time the image was taken. They were informed that all images were taken between 2010 and 2014, and half of the images depicted individuals over 21. We use this task because everybody thinks they have roughly the same clue. They're all of us judge ages all the time. And we can do it very fast. We don't think that much more concentration is I'm gonna be able to really parse it out. You'll see why it's particularly difficult in these cases. It's a hard task because many of the people are wearing makeup and they're trying to appear different ages than they really are, and they're quite successful. So what's the probability the person in this image was over 21 years old? That's a question. And people had time to complete it. And then there was you click on the bar to move it around. This is the experimental interface. Participants in the treatment group are also shown an AI assistant guess in half of their rounds. And the AI assistant is a little bit better than a typical individual, and it's a well-known algorithm. Again, it's very upsetting how hard it is to find cases, given that Google has 600 million that it could offer, but it's offering them inside. There are all kinds of groups that could give us tons of data that we could be analyzing, but it's hard to get them to agree to give it. So we've got now some public cases. The age database is very famous. The age algorithms are well known. And this age algorithm that we're using was better than the average, but worse than the most skilled human. And the way...
Sorry, can you tell us the actual numbers?
Yeah, I'm going to show you.
Oh, for how well they do. Okay.
Yeah. I'm going to show you. But here's what the AI advice says. An AI assistant guess is 62%. Now you guess. We ran this on Prolific with 500 participants in treatment, 250 in control. There were practice rounds. We had 160 incentivized rounds, followed by Raven's progressive matrix, and 80 untreated, 80 treated. Participation bonuses for being correct according to a binarized scoring rule, and bonus for getting the IQ test question correct.
And can you explain a bit of design? Why did you not tell the subjects how accurate the AI is, how accurate the average human is?
We told him it's calibrated. We told him it's calibrated. We tried to indicate it's calibrated. In other words, if it says 61%, 61% is the chance, roughly speaking.
But calibrate doesn't tell me anything about whether it's more accurate than the average human and by how much. It seems like I would learn a lot. If you asked me to do this, I would really want to know not just that it's better than the average human, but how much better does it perform than the average human? What percentile of humans performs it? That seems like, to the extent that this is about to the extent you want to be citing Otter and Acemoglu and think of this as being about genuinely integrating this in the labor force, you'd think when you give me an AI assistant, you tell me a fair bit about just how good it is and how good it is relative to, because I'm going to condition a lot how much I rely on it depending on these numbers, which now I have such a diffuse prior over.
I certainly think it's a worthwhile addition. I'm perfectly content to kind of think about. In fact, I would find it very interesting to vary the statement and the quality and see how it worked. I'm not disagreeing that could be a wonderful, I'll call it refinement. But you're going to see our result is very clean.
What was the difference between treatment and control?
The control people went through without any AI treatment ever, because we wanted to see if there's deterioration or improvement in performance in various levels. There was a group of people and then the treated people had the AI assistants for half the rounds. And
the half the rounds for the treated people were randomly distributed through the 160 rounds, or came first? It was done in rounds. There was round 1, 2 with this, and round 4, 3, 4 with that. They were interleaved in terms of potential tiredness. That was the motivation.
Ben Weidmann played a big role in helping us with the design. Here's the thing that Emir might have wanted to produce. The actual performance of the machine. I think they were told it's better than the average, but worse than the best, and that turned out to be true. Without the AI, humans are clumped in their. So what we're going to do is the report closer to the truth is how we're, all of these get measured, and we're just saying, look, if you said 60%, then you were guessing, 60% over 21. That was a guess of over 21. How accurate are you? And it turns out that the machine accuracies were higher. That's the dotted line. And fairly standardly, they're even higher than the right-shifted performance with the AI. In other words, the AI seems to help people. But there are quite a few people who might have benefited by simply ignoring their own thoughts and repeating the AI, but they don't. They kind of have their own opinions and they add them in and they change. We use very simple measures of confidence. We've done several different variations, and confidence, the simple measure is were you correct more often? Was your average report of which is more likely, let's say I'm 90% sure, higher than the proportion of times you were correct, and we'll look for the average difference. So this is the most intuitive, but not the best necessarily measure of overconfidence. People who report that they are 90% sure, but are correct 70% of the time, are 20% overconfident. And this is the distribution. There were some people who were underconfident, but as is typical, there were more people who were overconfident.
Andrew, 9-10 minutes.
Okay, I'm doing great. Okay, is calibration related to performance without the AI? Well, what's going to happen is, if you take a look at the 3 in yellow, this says that when you split the sample in half, there's significant predictive power for accuracy. In other words, it's a fairly stable measure. Accuracy in one half predicts accuracy in the other half. IQ predicts accuracy in the treated images, and calibration does nothing. But when you think about performance with the AI, we have the standard finding that if you were more accurate in the untreated images, then the AI helped you less. That's the minus sign. But if you are calibrated better, then the treatment helped you more. So exactly the finding that is, the first finding is the standard one, that if somebody, that AI equalizes across skills, that you're helped more if you're low skill than if you are high skill, which is intuitive. And you're helped more if you're calibrated than you're uncalibrated, even conditioning on your skill and your IQ. And the biggest counterfactual is that the people who are helped the most are those who are low skill, high calibrated. And here's a picture of all the counterfactuals. You would 75th to 25th percentile range. If you are calibrated, and so let me just read this. If you are calibrated and use the AI, you would greatly benefit. The skill gap would the gap would halve. So I don't want to go into this because I'm not saying it exactly right. What's going on is the group that benefits the most. If Daniel's on, he could probably interrupt me and say it better. The group that benefits most.
This is your show, Andrew. I'll let you.
No.
Okay, well, I'll do it very quickly then. The leftmost column here says that without AI, there's the big gap between the 25th and 70th percentile in terms of performance. Then when you bring in AI, we get exactly what we see in the labor literature, which is a huge shrinking of the gap between the 25th percentile and the 71st percentile. But now we're going to do the standard labor trick, which is to imagine a counterfactual world in which we get rid of miscalibration. Now, without AI, there's still a huge inequality in performance between the 25th and 70th percentile. That's the third column. But the fourth column shows you what happens in this counterfactual world where you have no miscalibration and the addition of AI. And then AI shrinks that gap in performance inequality even more than it would in our regular world. I hope that wasn't stepping too much on your toes.
No, that's helping me. That's not a hurt. Okay, and I'm going to close with by pulling back just for a few minutes on what form of economic theory am I doing here, and is it really economic theory? And I want to say the answer is strongly yes. That it's a branch of economic theory that really picks up on production models. And both papers measure mistakes that matter to productivity and look for patterns in them. This is, I believe, a hanging chad. The economic modeling of productive efficiency is something that we backed out of as theorists long ago. Harvey Liebenstein would write about efficiency of firms in the 1950s. There are thousands of studies of inefficient production in a whole field called production management. 2 papers, including one by the great Gerard Debreu, and then also Mike Farrell, written by economic theorists, advanced the measurement of productive inefficiency. But economic theorists backed out because we have no expertise in factory design. Like, I don't know. I mean, just arrange it any which way you arrange it. And you're screwing up and call a production manager in to change it. So a very, very Stigler-esque dismissal of efficiency in a paper called On the Existence of Efficiency in 76 said, look, there's a problem with the theory of efficiency. And here's the quote. Waste is error within the framework of modern economic analysis, and it will not become a useful concept until we have a theory of error. Well, that's what we have nowadays. This form of theory is increasingly in place in rational attention theory, efficient coding, probabilistic distortions, and data innovations have also liberated progress. I've indicated why I think state-dependent stochastic choice will be central as mistakes are studied more. And these patterns in mistakes will be central in the age of AI, and theory will play a far bigger role in the age of AI than in the agricultural, manufacturing, and service economies. I mean, we're going to study mistakes in every single context. This is going to link with Marshak and Radner on information flows in teams, which can now be really operationalized, and studies of information design. And there are many next steps on tap. A model question. Well, I don't know how to model optimal learning for a probability distorter with and without AI. I do not know how to do that. And I think one of the main reasons that rational inattention comes in, while at the same time we know that people distort probabilities, is the mix is extremely sophisticated. And if you want to think how sophisticated, think, what do I do with an AI that says 0.7 if I'm a probability distorter and I also have endogenous learning? I don't know what to do with that. It's fascinating. How do we conduct experiments to pull the effects apart? A policy question, how can we teach skills such as calibration if they matter? But the method point in this area, I believe advances in economic theory will co-evolve with advances in measurement. Thank you.
Thank you very much. That was a fascinating talk. And thank you everyone for participating, and Daniel as well to chipping in. Now we are moving to the Q&A session, and let me start by our usual custom with our panelists. Are there any sort of last questions or comments on a more general nature? I think Larry is unmuted.
Yeah, I have two questions
Please.
that I would like to ask, or possibly two things to add to this list of further work. The first one is, Andrew mentioned that the reasons that people have for choosing the loss functions, for choosing the betas in these kinds of AI settings are, I think the word was wacky, which I'll think about the next time I have an X-ray. And then also mentioned that it looks from these data like large betas are counterproductive, and that we should push these things towards smaller betas. There seems to be a bigger question here. The data show that the choice of the loss function can affect how well the algorithm learns. And so cutting out the second part, let's not worry about the humans yet. Let's just think about the machine. Yeah. Suppose we're going to look at the machine. If changing the algorithm can affect how well it learns, we may want to push the algorithm away from our ideal, trading off.
100%. Absolutely, completely agree.
And so now
I don't understand that. Depends what the ideal is. I mean, let's take a concrete example of pneumonia. It seems like if we'll be using the algorithm, we're going to, for a particular function. So what we're going to do is we're going to send the images to the machine. Machine's going to give out a probability, and that probability is going to get mapped to a treatment. So if the probability is 0.8 or more, we give you antibiotics. If probability is between 0.4 and 0.8, then we order a human to look at it. If it's between 0.0 to 0.4, we let you go. That's the actual utility function we want. So we want to train, there is an actual loss function that this is being used for. So it seems to me that the first result, that you can't do better by using a loss function other than the one. You can't do better training on loss function 1. Your performance is never going to be better training on the loss function other than the one that is your welfare. Why would we ever do anything other than use the actual welfare loss function? That's not beta equal to 0.99. I agree, that's wacky, but we should always be, seems to be using the actual welfare of the agents that are using the output of the algorithm. That seems to me non-controversial.
It is controversial. It is controversial.
But
why?
Because
there's endogenous learning. So we haven't made a link there to what the algorithm actually learns. And it seems to have something else that we're not really very interested in, which we're calling its pseudo cost function, which is interfering. And and that we don't know right now, that's artifactual. We have some sense that it may, in certain cases, come from offering unclear guidance on the appropriate direction to travel, and this algorithm wanders all over the place.
I think our intuition easily leads us astray here. We're used to our economic models where we can separate preferences and learning. And then it's obvious that there's an objective standard of how well something learns, and we always want it to learn as well as we can. I have the sense that that's not the case here.
So maybe one way to rephrase your question is that let's just put the flexible, costly function aside. It seems like the intuition, I think, does not lead us astray. Suppose we actually know what we're going to use the predictions for, as in the pneumonia case. Now I could say, look, I know that this is my actual ground truth welfare function. Let me now ask, let me go and train the algorithm using various loss functions and use the predictions from those on the ground truth. So I don't know why we would ever do anything other. This is now just choosing the loss function can be just specified as a part of the algorithm. But the evaluation of the algorithm seems to be always what welfare does it yield when applied?
Well, what we're saying here is that in this manner of training where you fix an L, there is an implicit K, and the implicit K may have nothing to do with the welfare that you would like it to be maximizing. And it may interfere with what it learns because it says something is expensive. In this case, it certainly did.
I mean, that's your interpretation, but another way to put this is just, look, here is my ground truth welfare function. Find the algorithm, use the algorithm to train the data. Use that algorithm on the training data set with the explicit goal of, in the end, doing the best on the ground truth welfare. Now, it could be, and this would be an exciting observation, but that's an observation that doesn't have to be couched in terms of the implicit cost function, that training using a loss function, which is not the ground truth welfare, is better when training the data set.
So the interesting
is training the algorithm on the training data set.
So this paper suggests, interestingly, that might be the case and gives us an interpretation for why it might be the case. That if I give the algorithm my true loss function, it might choose a crazy K. I don't know what inside that means, but the results suggest that we can usefully view the algorithm in that terms. And so I might want to trade off my loss function a little bit in order to get it to choose a more sensible K. How I do that, I don't know, but I think
that's exactly right. And Emir, what you did was you added in a second stage in which I've played with all the L's, and now there's an L star which really has nothing to do with my original L. It turns out to be optimal, and you've said correct thing to do is use L star.
But I just feel like this is exactly what people what I'm not sure that this is that different from the practice of machine learning, and that these different L's are just sort of tuning parameters.
Well, I think that if you look at published papers, you'll find that they use an L. We do not know the search process.
So let me suggest we could talk about this forever, and I would be pleased to do that. Let me move on to another question. This one was previewed by Emir during the talk. You have this sequence of models that we can use to think about the algorithm. One has no constraints. The algorithm learns perfectly. One, the algorithm is constrained in the models it can use. And one, the algorithm has a cost function that it attaches to models. And there's a sense in which these are nested. As we move up this scheme, we get more and more explanatory power at the cost of a more complicated model. And I'm not sure how to trade that off. You mentioned in the paper that when you get to the cost function model, you're not rejecting the null, but your test has a lot of power. And so we feel...
I think it does. I mean, again, this is a thing that Daniel has thought a lot more about than I have. I actually think it's...
Yeah, so I believe it has a lot of power, but that's a statistical test. And what I would like is some way of thinking about the economic differences. I could imagine that I have a model that with enough data, I can, with extraordinarily confidence, reject as being incorrect, but it's economically close enough that it's worth using, even because of its parsimony. And that's a trade-off I would be
I'd be
interested in
interested too.
about.
I think in this case, so I'll tell you what happened. We didn't really have a clue what would happen. Honestly, we did not have a clue. We did not know whether a cost function would show up. We really did. We just kind of put it down as a matrix. It comes out, a cost function shows up. When we see the cost function, it becomes a little bit sensible. It says, oh my God, you overweighted. It was not a proper scoring. These are not proper scoring rules except for beta 0.5. You told the algorithm to say 99% to almost everything. So it does. And it doesn't differentiate between 0.993 and 0.994. It's not really working very hard on anything there. So what happens is it actually does bad learning, kind of because you told it to. And we only realized that at the end. Like, oh, wow, why is it learning so badly? And that's what's going on. They don't even bother in the literature discriminating all that much between proper and improper. They don't care. Like, I don't know. It's a loss function. It's got parameters. What's your problem? So even just thinking the word proper, they'd say, well, I mean, yeah, if a human's going to use it, sure, but who cares? But Emir's program is like, give it a real utility function. That means give it a loss function that, in which what it says is at least honest.
I guess one thing, this is the last thing I want to say on this, because we did talk about it a lot, but let me try to phrase it differently. There's a way of phrasing your empirical finding, which is unrelated to economic theory, and therefore I understand not part of your agenda. But it could, but I would love to hear the feedback from practitioners in machine learning if you say the following. Suppose that your goal is to minimize loss function L1. That's your goal. Here is what I am proposing you do. I'm proposing you use your standard algorithm, but endow it with loss function L2. You do better than L1. Couple of questions. Is this news in machine learning? Is this something that everybody's going to say, yes, we understand that? Or, wow, really? Okay, this opens up, when purely outside of economic theory, an agenda of, if I want to, in the end, judge the performance of an algorithm with L1, what is the L star of L1 loss function to train the algorithm on?
Yeah, I mean,
I would love to take this question because I've actually talked with a lot of practitioners, and there are special cases where they are not surprised by this at all, like a discontinuous loss function. Like they can spot that something's going to go wrong when you train a machine with a very discontinuous loss function. So they understand that there are classes where sometimes you want to train what they would call maybe a surrogate loss function. But more globally, they're not thinking about the design of loss functions from a theoretical perspective. So they're not thinking about, oh, hey, what would incentivize this machine to do the best kind of learning that we would want it to do? They're going to say, let's choose the 5 regular loss functions. This is my class of loss functions I'm going to search over. And I'm going to see, oh, squintropy does the best in this, not something else.
So I noticed the word incentivize came up there, which I applaud. I think that's a good answer to these last few slides. Why is this economic theory? This strikes me as a whole wonderful new sandbox that we can play in.
thank you.
I think we're almost out of time, and we're supposed to give others a chance to ask a question.
So, Emir, is there anything you want to add in the allocated recorded time that we still have? All right. And anyone wants to ask the last question before we turn into the unofficial, unrecorded phase of the meeting? Any other questions from the audience? We have a question. I have to report it. A question from Francesco in the chat. Why so many rounds? We can talk about this now or later.
That's
Oh,
not
you mean
okay.
It's a different Francesco's, not me.
Right.
well, you've got to get a fairly heavy use of the scale to hope that you have a stable notion of skill and a stable notion of calibration.
Okay.
So maybe I have a
Enrique.
question, if you don't mind.
Please.
So this is a bit related, but I would imagine that maybe we think about this machine learning being used for many different decision problems, right? So you have multiple utility functions. So you're going to decide whether to give an antibiotic, but you're also going to decide whether to quarantine the patient or something, whether to intern them in some high risk unit or something like that. And so if you think of maybe a decision problem as like a distribution over decision problems or a set of decision problems, then maybe a misspecified loss function might be inevitable in a sense, right? But have you guys thought about that in some sense? How we use these algorithms? Yeah.
Right now, I mean, first off, what they're actually doing is better described as wacky or cockamamie than thinking deeply about the 76 uses to which this algorithm might be put and compromising effectively given all those uses. I mean, they're just kind of like doing stuff. By the way, my bigger answer to get engaging actual people in machine learning is that they're busy on unsupervised learning and developing large language models and video training. And, they kind of think that these questions are like, I don't know, they're not the sexy ones for the computer scientists right now. So, but for medical decision making, this is still what's going on, absolutely. So I mean, like, I don't know, people are dying because this hasn't been done properly. And and as you know, the answer, the supposed ideal answer is think of all the ultimate uses, work out which actions you're going to take, and come up with an EU maximizing Hugemer given every single option that you have taken account of and what the beliefs translate to. So that's Emir's answer, is think about all the conceivable uses and come up with an EU maximizing learning given.
Yeah, I guess. Sorry.
Yeah, please.
No, I guess I maybe I phrased it in a confusing way, but I was thinking of something like really a theoretical question. Like if I have two utility functions and I calibrate the model, and I can only calibrate the model with using one loss function, then how is this optimal loss function related to the two utility functions? Like if I think with probability 1/2, I'm going to face one decision problem, with probability 1/2, I'm going to face another decision problem. What is the optimal loss function?
I don't know. I mean, but we haven't done it for a single one yet.
I see. I thought that your result said that given a loss, if you have a true loss function, then the best you can use is the true loss function to calibrate the model.
No.
Okay.
No, that's the discussion we've just been having.
Okay.
We can't tell because there's this bizarre pseudo cost it's throwing in its own calculus, which has nothing to do with us.
I see. Okay.
All right. Thank you very much. I think it's time to close the official part of the meeting. So thank you again, Larry, Emir, and Daniel for joining us, and Andrew for giving an excellent talk. And see you next week. And while the